Hi everyone, welcome to ConnecTechAsia and another session, I guess, that be interesting to see how this goes. It's about LEO, the challenges of LEO. First of all, before we worry about the challenge, it is an exciting moment in time. This is quite something. For me, getting on the wrong side of, way past retirement and beyond, it's interesting now. I still think I perhaps should have gone into rockets when I was small. It would have been exciting now as it would have been then. But LEO is exciting, and as a piece of technology, I'm excited about it, and I want it to work. But there are challenges, and even this week, SpaceX has said about the fact it's launched more satellites, it's got inter-satellite links, it's working, but even they use the word challenges. So my thinking is that we're still a little bit at what I think is in the experimental stage of LEO. It's up there. There's some of it's up there, and SpaceX obviously is taking the lead. It's got numbers. It's a big network already. But I still think it's going to have a limited effect at the beginning. I think, and anybody can put me right later on about this, but we're probably looking at North America being the place where things get tried out. I think it's going to be that area that gets it first. We know that SpaceX is already doing test transmissions between some staff members on the ground to see how it works. And, so that's interesting. But from us here, and we've got everybody that supplies kits, the hardware, the ground infrastructure, which is an interesting challenge all in its own right, from Violite and ETL systems. Also, we have Kratos Online, which cover an enormous range of aspects for LEO anyway, and of course leads me into the great wonders of how on earth do we manage transmissions from these like we do in GEO and MEO at the moment from a problem point of view, incidents, problems that happen when we have services. So I'm really interested to start looking at that challenge. Where are we? Are we ready? And we've got a satellite consultancy online to look at operations and think about how we're going to manage this between satellite operators. And I guess the problem is here, and probably for all four of us, I think we all have knowledge of LEO, but I think we've got a lot more to learn. I think we're starting to run before we've learned to walk, perhaps, in this subject. And probably the real thing is we've got to start learning about these systems and really understanding it. Equally, I think the LEO operators have got to learn too. They've got to understand where they fit and the fact there is a system out there, there is a process, there is something they have to do. They have to manage their lot and they have to manage it with everybody else, all the other satellite operators. So who will we call? Who will we ring up when there's a problem? How do we do that? So before we get into some of that, and that could lead to a nice bit of Q&A eventually for this session, I think we'd like to start now with Violite and their presentation, and from Richard Jacklin. So Richard, over to you, sir, to start us off in the realms of probably the ground infrastructure and how you see things from a LEO perspective. Thank you, Richard.
Thanks, Martin. So I'm going to share my screen. Just got a couple of slides. There we go. So just very quick introduction. So I'm Richard Jacklin. I'm from Violite Communications, part of a company called PPM. Violite is based on a technology called RF over fiber. And you'll see us in the SATCOM world. We essentially link antennas and dishes back through to control rooms, and we can do that on a sort of typical gateway or teleport site, distances of hundreds of meters, and we can also link diverse sites, particularly in the Ka bands. So if we've got two main antennas, one sort of primary, one redundant, we can link those back to a control room, and that link can be about in hundreds of kilometers. So it's a specialist kind of technology. We use specialist lasers and photodiodes to take RF signals and transport them over optics over great distances. So that's kind of the technology. So we're kind of you know, a part player. We don't provide all of the ground segment, but we play, you know, an important part in that makeup. So talking about LEO, so this is really just following on what Martin was saying about, you know, what we're learning, what we're adapting to, and how we're kind of satisfying the market. You know, obviously the conversations and the projects that we're working with in the LEO area has created a certain, I'd say, a number of characteristics which are different from the kind of traditional geo business. So obviously LEO, I mean, we all see it in the press, the scale of this rollout is on a volume much higher than what we see in terms of geo, in terms of actual numbers of satellites and gateway ports. Where we're dealing with the LEO operators, you know, each constellation can have tens or even hundreds of gateways per constellation. And there are lots of constellations in the planning stages and you know, the initial launches that we've already seen. So volume is high. Each of the gateways, these are interesting. So we're not talking about like one giant dish here. We're talking about a cluster of dishes. You know, obviously the industry is trying to get flat panel. Most of the solutions we've seen at the moment are moving parabolics, but we're seeing these cluster of dishes, and they can be anywhere from 5 dishes up to 25 dishes in a cluster. So, you know, if we take a small cluster, for instance, you know, we can have 4 tracking antennas. We have possibly another antenna that is doing handover, swinging across back to the other low elevation, and we probably have a redundant one. So at least sort of 6 antennas in a very minimal setup. The other characteristic is, you know, we have this cluster of antennas, and obviously they need clear line of sight to the antenna, to the satellite. That's clear. So there's careful interference management in these gateways, in the sense that they shouldn't be self-interfering with each other, because LEO, you know, works close to the horizon, and the elevations are very low. You have to be careful in how you arrange these clusters so that the antennas don't actually self-interfere. And also because of this kind of low horizon element to it, it means that these dishes are pointing close to terrestrial communications like cellular and other high frequency systems. So you have to be careful from the RF interference management as well. And of course, you know, with lots of comm systems, you need a gateway that is close to a point of presence or a POP or an edge POP, which are typically kind of fiber-driven locations. So from our learning, our experience, I suppose, this throws up a number of challenges. I've got 3 challenges here. There are probably a lot more, but this is just what we've come across so far. First is the antennas. I mean, there's lots of these antennas. They can be quite small. I mean, if we look at the parabolics, they're kind of in the range of 2 to 3 meters in size. They're small. So if we're connecting through to these dishes, you know, the products that we produce now have got to be smaller form factor. They've got to be reduced weight, you know, produce less loading on the back of the antennas. So size is key, modularity is key, and I've just shown a typical product on the right-hand side. I'm not using it as a sales exercise, but it's the sort of thing that we've been supplying. Second challenge is bandwidth. Of course, you know, our satellite industry has been moving up frequency spectrum. It's increasing bandwidths, and that's still the same for LEO, of course. So we're looking at large bandwidth chunks, at least 500 megahertz. Some of these are into the gigahertz. So you need linkages which have got very good dynamic range in all parts. And the last challenge is the actual positions of these gateways. So ideally, you want to put a gateway right next to a POP where you can get into the fiber network. You know, you might need 100 or 200 gigabit connection into the POP. Sometimes that's not always possible because of geographies. Again, these LEOs, you know, they need to see the horizon as close to the possible horizon as they can. So sometimes you need to position the gateway away from the POP. So that means you've got sometimes large distance, and that could be tens of kilometers. So moving large quantities of megahertz or gigahertz information across long distances is a challenge. obviously, from an RF over fiber perspective, that's where we come in, because we can do that quite efficiently. So they're probably the three challenges I wanted to bring up, Martin. I can stop sharing. There we go.
All right, Richard, thank you. That's good. It's interesting. It's interesting about, you mentioned interference management. You managed to bring the I word into the conversation. Yeah, yes. Well, I hadn't thought about it from on a local basis, but it interests me because I see a ton of places when you've got such a large infrastructure to put in for one of these networks. It does wonder how many types of incidents and issues we are looking at here, both from space point of view and within the ground infrastructure itself. So thank you for that. That's interesting. So to quickly move on so we can get the next perspective of a supplier's point of view. Andrew Bond of ETL Systems. What's your view on this? Where's ETL in this? Obviously it's in a similar vein to Richard. You're in that supply chain, but it must seem difficult in terms of what you've got to supply to these guys to make it work. And are they teaching you what's going on to make that better, or is that just an uphill struggle for a company like ETL to learn what they really want from a system? Andrew.
I wish I had a crystal ball, Martin, to be able to work out what is going on in the LEO environment at the moment. So we're having to make some quite big assumptions without knowing that these test situations that you referred to are actually working 100%. Richard mentioned multiple ground segments, and depending on the number of birds that are flying, these could range anything from 20 to 40 per constellation up to the numbers that Richard mentioned. And I agree with him. We have to make assumptions that the bandwidth is going to be slightly higher. And we see people pushing up to Q and V bands. It's going to have to be handled. We're also making assumptions that there's going to be a number of tracking antennas on the site. And we're making assumptions that we're going to need to handle uplink and downlink feeds. So from ETL Systems' point of view, we're having to sort of second guess what is going on while this test phase happens. And there are some very big players in the market, not least SpaceX and Amazon and Telesat. But it was good to see that OneWeb was rescued the other day, and that is back as a major player again. So we're pleased that the investment is being looked at, and it's being looked at seriously by countries, not just in America. So ETL know that we're going to have global connectivity, and the issues are at the moment that it's being driven heavily by the need to supply broadband. And I still have a big question for this particular seminar as how people are going to deal with it not being allowed in all countries, especially in terms of ground infrastructure. So, certainly flying LEO over certain parts of the world will have zero connectivity, for example. So from our point of view, we've got to make some advanced designs, hoping that they're the right things for the market. So ground infrastructure is going to need very fast switching, and we've got some products that allow us to do that, both for uplink and downlink. So, we're receiving a signal into the ground segment from a number of steerable antennas. We've got probably 10 to 15 minutes of good signal per antenna before the line of sight fails, and we have to hand over to another satellite. And I think I agree with Richard, we need to be seeing modularity, because not all ground segment teleports are going to be the same. So we're designing chassis which house not only switch matrices, might house frequency converters, fiber modules, and also splitters if people like Kratos need to monitor those signals remotely via Ethernet. So this size and modularity are important for us. But finally, it's the cost pressures. I mean, teleports historically are pretty good at spending money, and that's has meant that companies manufacturers around the world have done well. We've grown 10 times in the last 10 years. It's great to see the market and the satellite world giving companies like us a sort of a boost. But the mindset to cost pressures for a LEO satellite teleport ground station is going to be very different to the ones that we're used to with these big chunky antennas. So cost is going to be driven way, way down. And again, I agree with the previous presentation that we're looking at trying to manufacture a modular kit at a much lower cost than we've ever done before to switch RF, fiber, and whatever other signals are required to be moved around a ground station for uplink and downlink and monitoring traffic. So in summary, we're in a good place, but I'm still looking into the crystal ball with the rest of my team to understand and watch carefully exactly how these early adopters what the results of these early adopters are going to be. And hopefully we're in a good place to respond to those. There you go, Martin.
Thank you, Andrew. That's good. I like the thought about the landing rights issue. That's always an intriguing one for me, about where they're going to put all this ground infrastructure and how on earth they're going to deal with it on the cut. I mean, perhaps Yoshi later on, that'll be something that's probably in your mindset about how on earth this all manages and how people are going to do that. But perhaps that's not such a worry to us. That's more of a business case issue. But how are they going to control this? Probably leads beautifully to Bob. He's probably got even more breadth in this in terms of technology from, well, as Andrew mentioned, everything from monitoring this animal. And thank you, Andrew, for reminding me about Amazon. My friends and colleagues in Amazon would have killed me if we hadn't mentioned that word. So thank you for that. Because that's another big player to come. And I think that's probably one of the more serious now that perhaps wasn't in the game at the early stages. And we got rather used to the SpaceX's and OneWebs and Telesats, when now I think Amazon has probably started to shift up there. Little ways to go there, but anyway. So Bob, you know, Kratos, huge, probably deals with all sorts of aspects of LEO. Probably been a tough learning curve. Well, you probably understand it technically. In fact, you know, out of all of us here, I think probably Bob's right in there, especially when you think of things like geolocation, how to monitor services, and speed when you haven't got much time to do it. Well, perhaps you can take us into that, where we start to join from the hardware on the ground and looking at the management of space, and then lead to Yoshi, who's going to look at, you know, the actual operations side of things in the end. So, Bob, over to you. Thank you.
Thank you, Martin, and thank you all for attending. I'd just like to, well, this morning I'd really like to concentrate on the spectrum aspects of LEO. Within Kratos, we do address lots of different areas on LEO. I guess everything except the RF elements, which are the two things that have already, the two things that we've already been speaking about in terms of amplifiers and transfer of data and so on. But all other aspects Kratos can address, but and it's such a wide-ranging topic, I thought I'd just concentrate on the spectrum side of dealing with LEO. So the big advantage of satellite communications still is, and always has been, is the ability that we can transmit large amounts of data to anywhere on the planet. You know, that's not necessarily easy, but it is proven that that's the big advantage of satellite. And LEO is hoping to add to that advantage by essentially providing a low latency aspect to that communication. And in fact, there have been studies by various eminent universities that have shown that even the latency through a LEO satellite network would actually, if we were going coast to coast here in the United States, would actually provide less latency through that network, through a double satellite hop, than going through a fiber network. Seems strange, right? But most fiber networks are not actually point to point. You have to go through various switches and so on, which adds to the latency. So now satellite can actually challenge a terrestrial network in the traditional sense by providing low latency, wide bandwidth anywhere that you want it. So it all sounds great, right? But just like our cell phone systems, we all use radio communications in order to make that happen. And in the world of radio communications, all kinds of things can happen. So just but to kind of emphasize the complexity of LEO. So we know a traditional geo world, a geo operator will get a single slot, which is a fixed slot above the equator, and they get the rights to use a certain amount of spectrum. And that's pretty exclusive by that slot. But that doesn't mean to say that their neighbors don't have equal frequency rights in the same frequency band. And the way in which we mitigate, let's call it border disputes, if we're using terrestrial terms, is that we have large antennas with high directivity, which means that we mitigate any of those border disputes, or what we call adjacent satellite interference, if you like. And in the LEO world, how that translates is they're really translating that in terms of orbit. You know, we have highly directional antennas, which are tracking the movement of a LEO satellite. And the fact that all the LEOs are in different orbits, great. We mitigate those border disputes. But it's not quite that simple. We've seen that I think all of the four major constellation proponents are advocating hundreds of satellites, anywhere from 400 satellites up to 4,000 satellites, depending on who which operator you're talking to. And they don't all operate obviously in one orbit, and they don't even operate all at one altitude. They actually operate in what we might call shells. And so there are hundreds or thousands of satellites in a single shell, which is a series of orbits which are a fixed altitude. And then there may be a similar shell, which may be 50 to 100 kilometers higher, and then in some cases even a third shell. So of the four major operators, we've probably got 10 to 12 different shells of satellites sitting up there, all orbiting the Earth in slightly different orbits. Add to that they're all advocating, at least from their FCC filings, they're all advocating the use of Ka band for their gateway communication links. It's interesting that two of them are actually advocating Ku band to communicate with the general public, i.e. us, and two of them are advocating Ka band to communicate with the general public. But they are all using Ka band to take advantage of the bandwidth for communicating from the gateway, from the satellite access points, if you like. So at first read, you might think, oh, crikey, this is just a problem waiting to happen with all of these satellites moving around, all transmitting the same frequency. And I think the answer is yes and no. So if we first look at the LEO interference, well, you know, really that's kind of I would treat that as an in-house problem. As one satellite passes either in front or behind another, as we are tracking a given satellite, that duration is going to be quite low, and can be managed, I believe, within their own management systems. And I'm thinking that if an operator can manage the three shells of their own network, they can manage aspects of dealing with their potential competitors. I think the main concern comes with when we go to LEO-GEO communication, because GEO is also using Ka band. And they have all filed different details of how they will manage LEO-GEO on a non-interfering basis. I suppose the most talked about is the OneWeb version, where they're switching the satellites up, and they have this tilting mechanism where they tilt the satellites away from or back towards the equator, depending on whether north or south, the satellites will tilt, but they tilt back towards the equator. The other constellations are really dealing with it on the basis of we have lots and lots of satellites, so therefore our look angles will never be low, and never be pointing back towards the equator. So we'll always be communicating with a satellite at a very high level, elevation level. That also has the aspect of being able to mitigate any potential terrestrial type interference coming into the satellite antennas. That in itself it seems to be pretty well thought out. But the aspect is that you have fixed antennas in the LEO world, in the GEO world, pointing at a GEO satellite, and we have LEO satellites transmitting the ground to the ground surface. Now, the ITU has prescribed a set of rules that are detailed in Article 22 that we will only have so much energy and so on. But we do have the potential that maybe, maybe 10 satellites or more will be lighting up or transmitting energy into the same spot on the ground. And what does that really do to that LEO antenna, to that GEO antenna, I should say? There are thoughts that it might just raise the ground temperature, if you like. And those of us who are interested in the ground segment, G over T is a big thing, and we really worry about G over T. And if we're raising the background temperature of the ground effectively by transmitting so much energy, albeit from different directions, and potentially coming to the backlobe, are our specifications enough? Well, I suppose the upshot is we have our specs and we have our rules. We just need to learn to live, to work within those rules. And so the challenge from Kratos' perspective is in monitoring the spectrum, not so much from LEO to LEO, as I mentioned. I think they will take care of that themselves. That's an in-house problem that affects their network performance, which is really what they're selling in terms of bandwidth and latency and so on. So they will take care of that. I have no doubt whatsoever that will be taken care of and will be managed within their in-house management networks. The LEO-GEO aspect of that is really about how do we provide tools and information, and not just here's a pretty picture of a spectrum, because what does that really tell you? It's actually taking it further into here's what's going on in the frequency spectrum, here's where the energy is coming from, and here's what's happening. And presenting the data in such a way that the various organizations can now sit around a table and talk sensibly about the data, not necessarily talk about how the data was achieved or who's in or out of the rules or whatever, but how can we make these systems all work and live together? And so that's really where our focus is designing our systems. Now we have some experience with the LEOs that are already up there in capturing the data, processing it and presenting it in such a way that it can actually be made use of by the various operators in order to make everybody's system better. Thank you.
Yes, it's all right. Sorry, Bob. I had to go and find the unmute button there. Thank you, Bob. I mean, that brings an awful lot of thoughts to mind there. I mean, the other thing I think that's probably missed there is what about one LEO constellation, the effects to another LEO constellation? And you mentioned ground noise, G over T. Whilst I have a better view of that than most, but when you think about it, are we going to see pulsed noise problems from not just a constellation, but obviously having several constellations up there? You say, 12 shells of, a major set of satellites in each. I see like a pulsed noise problem coming up that would be regular, probably repeated, and probably you can find out how to do it, and maybe there are ways of mitigating that. But I see this type of technical challenge, and like you say, how on earth do you display that? How do you make it real data that can be sorted quickly to tell someone else what the problem is, and share that data so that in some way so that someone else can fix their own problem? Because as we all know, and this leads nicely on to Yoshi, who's been at the sharp end of this for some time in his working career, is eventually someone's managing a fleet of satellites. Let's not worry about where they are at the minute, LEOs, GEOs, MEOs, whatever, but he's managing them. And like everybody, he's managing his bit, and he can look after his bit. Like you said, Bob, we can manage the LEOs within the LEO of the same constellation. We think that's pretty good. But in terms of someone else, I wonder where we sit there. So Yoshi, with all that wealth of experience and sitting at the sharp end of looking at tools from Kratos and all sorts of stuff over the years, what's your view on the challenges from probably a satellite operator's point of view, whether you're perhaps whether you got your LEO hat on or probably your GEO hat on? So Yoshi, take us into the next part of this puzzle.
Thanks, Martin and Helen, for inviting me on this session. I don't belong to anybody at the moment, but I've been working in mostly in the satellite operator domain of the industry. And well, sad to say, I don't have much experience in the LEO aspect, but I have some experience in the GEO. And as a GEO satellite operator, my concern would be interference with LEO GEO satellite interference is my concern. When I was in Japan, I did some analysis of WiMAX interfering into satellite. And as you know, WiMAX is just a terrestrial network. But when you accumulate all those spectrum by consumers, millions, billions of spectrum piling up, it increases the satellite noise level. So my role was to properly coordinate with the terrestrial service providers, mobile providers, to have enough guard band between the spectrums not to interfere with each other. So my understanding is that the LEO spectrum will eventually start interfering with the GEO spectrum. And in order to mitigate these interference risks, we need to have a comprehensive way of solving these problems. And when you talk about LEO satellites, they are low cost in launching, low cost in manufacturing, but they have a huge cost in ground segment. So in order to mitigate those ground segments, there are service providers, startup companies. For example, in Japan, there is a startup company called Infostellar. I don't represent Infostellar at all, but they have this comprehensive software system that gathers the ground system information, and then they lease these ground segments to the proper satellite operators that require a certain timing. As you know, the LEO satellites rotate around the Earth. They need a global capacity of ground segment. And as Richard and Andrew were pointing out, these ground segments, each ground station needs a highly sophisticated tracking system. They need a highly sophisticated switching system. And if one player needs to create and also manage all these ground segments, the cost will not be profitable for the LEO satellite operator. So these kind of Infostellar solution providers would become a very essential element of the whole ecosystem. And I think in the long run, the GEO satellites operators need to engage with these service providers, to engage with the whole LEO satellite operators as well, to gather information in a anonymous basis, so that we can, the GEO satellite operators can mitigate, and also LEO satellite operators can mitigate the interference, which is essential for communication links as well. So that's one challenge that I have on my table. Also, if we can, we would like to have some LEO satellite operator technical engineers to come on board the SDA. SDA is, as you know, is a space data association, which shares the not only the ephemeris data or the orbit data, but also communication link data, interference data as well. So that might be helpful to put LEO operators on board. So I think, more communication, more talking between these operators would be necessary in order to have a clean spectrum in the long run. So those are the challenges that I have, particularly from a satellite operator's perspective.
Thank you, Yoshi. Well, that pretty much that wraps this whole subject up, and everybody's got to worry. I mean, there's no doubt about it. And I mean, you brought up the SDA Yoshi. It's interesting. If anything, their remit has actually shrunk a bit into, to give you some idea how concerned they are from the geo, so we say geo-MEO perspective, is that they pretty much hunkered down into the collision problem. They pretty much got themselves into a point where the reason they exist is now to worry about all this stuff going up between them and the planet itself, because it's in a critical area and nobody's sure about how well all this will actually go in terms of sheer numbers. They keep saying how big space is, but it's getting a bit tight in this bit. Space is big everywhere else, but not in the bit that Bob described in all the layers, which are only 100 or 200 kilometers, apart per shell, let's say, even taking one shell, and it's more complex than that. So the SDA is also sees a problem, but sees the collision problem. It sees that as the big issue, and debris and all the rest of it. So we won't go there perhaps at the moment, but it was just to set the scene that the SDA, I don't think, does enough. And that's another problem, because something that Bob said, and something, in fact, Andrew and Richard also commented on it briefly, although I don't think they tied it up at the time, is that Bob, if we take Bob as a supplier of monitoring systems, he needs data. So people that supply hardware need to make as much data about what their equipment's doing or anything else available to something else, whoever's monitoring it. Equally, a satellite operator could really do with sort of having shared data somewhere else that could see the more global problem of how other satellite operators are running their own fleet, so that they could see a problem perhaps before it happened. But guess what? We mentioned the word sharing data. Ooh, well, we all know how difficult that is, and I don't think that one's going to get resolved in any time soon by the time a set of LEOs gets up there. But maybe LEO, if they want it to work, it's going to mean for once our industry gets its heads together and perhaps creates a sharing environment. So stepping back from Bob and Yoshi a second, back to Richard and Andrew, a sort of open question that, where are you going in trying, you see the bigger problem above you. You're supplying someone else's ground or pieces of a ground system. And you've mentioned, obviously it's got to work and it's got to be modular, it's got to be tight. Andrew, you mentioned the fact about getting data out of equipment, to monitor, for someone else to monitor. So where do you think, now you see that top level problem, how do you propose working that into your hardware situation? And is it time that people like Violite and ETL, I know you compete, but is there a need to join forces a bit so that the people that ask for all this equipment need to talk to a body, even if it was like ourselves as SIG, but to someone that starts gluing this together? Because I don't think we've seen anybody from any of these systems, certainly not come into our room and talk technical. I haven't seen that happen once in years. And therefore, that must make your jobs harder. So Richard, Andrew, you can fight it out on the microphones, you can unmute and have a go, but what's your perspective now?
Well, I think...
you go first, Richard.
Okay, thanks, Andrew. Yeah. I think we've spoken about this before, about the differences between the satellite community and like the cellular community. The cellular community are very well used to putting standards, standardized interfaces for monitoring and testing purposes. And that's something we kind of lack really in the satellite world to have as a standard. I mean, us as a company, I mean, we're only a small part of it, but even in our world, this affects us in a number of ways. I think, first of all, it's making sure that any equipment that we supply has monitoring facilities on it. So whether it's the actual RF channel itself or characteristics about that, we have to ensure that that's embedded in. So we've got hardware pieces that can do that, but we try and build as much software element to it as possible as well, because that's the way the world's going, right? So the more that we can put in the M&C world, the better. I think the other element to it is, a bit about the switching side. So, I mean, we do diversity switching primarily at the moment because of rain fade and things like that. But that intelligence that needs to come into making switching decisions about which antennas you use is going to come into this from the interference world as well. So, it could be a big AI type project, but that something like that is going to be necessary because it won't just be raindrops that are affecting switching. It will be interference patterns as well. And I'll just finish there. But one thing I was going to mention back to Yoshi when you mentioned WiMAX, because that's just bringing back old days for me. It's made me think of something that's potentially on our horizon as well, and that is that the cellular world, the 5G rollout so far has been sub 6 gigahertz. The bit they haven't rolled out yet is the millimeter wave. So like if you look at Verizon and other people, we're looking at 28 gigahertz or other things. These are frequencies that are right smack bang in the Ka band that are going to hit the LEO. So that's really sparked my interest.
Okay, well, that's it. Andrew, go ahead. We need to wind up. So it's sort of concluding statements, I think, because this is a big conversation and 40 minutes was never going to cover it in a million years. Even just between us guys, we would have gone on for this for hours. But Andrew, a point from you, and then I'll move over to Bob.
Fine. Yeah, I've got a couple of points here. I agree that we need to look at redundancy. I think where single points of failure are not accepted within the telecoms world, and certainly in the SATCOMs world, we are seeing a big growth in a reduction in single points of failure. So a lot of our carrier handling equipment, the RF carrier handling equipment, automatically comes with that switching, and also providing the likes of Kratos with the feed, a copy of that feed, so that they can monitor the quality of that signal, whether it's signal level and frequency and the rest of it. But the main thing from ETL, and obviously I'm talking to you, Martin, you've just handed down a position as chair of satellite interference, and perhaps this is your time to come back to the market, to become, chair up the LEO coordination group, to bring these disparate bodies together to actually have that sort of common standard, that market standard that it sounds like we need.
Okay, well, there's a challenge. That's an action point I think I get out of this. I wasn't supposed to have action points, but thank you, Andrew. I will take something on. Helen, note that down. Bob, I mean, something that occurred to me in all this, and we probably can't cover it, but Richard mentioned it briefly there. Everything must be software defined to manage to move forward. I think that software definition has to be in everything now, because hardware is one thing, but it's got to be more flexible than that. Otherwise, we can't change it fast enough to suit whatever problem we come up with. So, Bob, comment from you, perhaps?
Yes, totally agree. One could say that 5G is a reincarnation of 4G, but in the form of being software defined. And standardizing on hardware across the elements and minimizing the effects of hardware in terms of the network is essentially software defined. And it'd probably be no surprise to think that the LEO guys are going exactly the same way. To come back to the point of Richard and Andrew, is there probably will be only one digitizer per antenna. And then we will do everything from that. It'll be fed into the modems, it'll be fed into monitoring systems, it'll be fed into tracking systems, and so on. There will only be one digitizer, whereas you look at the good old days where everybody showed up with their own acquisition equipment, and you had splitters, supplying feeds to everything. So that is going to change. What I think will be interesting, I think, to see over the next few years is whether RF over fiber or on optical, or RF over IP will win out. 5G has got their own standard, which is eCPRI. We have VITA 49, which is kind of more of a defense industry standard here in the United States. Will that be the way to go, or will we continue to use fiber? And obviously the advantage of fiber is bandwidth. And so that's something that'll be interesting, but certainly the software systems and the management tools will all be virtualized. And the advantage of virtualization is that you provide resources exactly where they're needed. And that's the world we're moving to. I think lockdown, if nothing else, has shown the world that we need to be able to adapt and put resources exactly where they're needed as that shifts. And you know, there are large swaths here in Silicon Valley of buildings which are closed, which we don't need internet bandwidth, but we need it all in people's homes.
Yeah.
So the
look at us now. Look at us all now. Exactly.
Yes. And so I think through VHTS and the LEOs, satellite industry is moving to a virtualized environment to, I wouldn't say compete, but complement what will be 5G. And we need to embrace that and provide the tools to make all that happen.
Thank you, Bob. And I get a last comment from Yoshi. I'm going to make it easy for you, Yoshi. So, putting your satellite operator's hat on in Mr. Geoland, are you a comfortable, no problem bunny, or is this still a big worry?
Of course, the answer to that is a huge worry for me. But as Andrew pointed out, I think we need to have more communication going back and forth between all the satellite operators to exchange what can be exchanged in order to mitigate all the risks. And also, as Bob mentioned, there's not only HTS, but now it's going into VHTS, and everything is becoming more complex and more, the frequency reuse, spot beam technology, everything is becoming so complex that it has to be virtualized, and maybe those meetings will be like AI versus AI someday, but the complexity is really becoming an issue as well, to just manage the spectrum itself. So talking to each other, sharing data would be one essential thing that I have in mind in the coming years. So yeah, that's my comment too.
No, thank you, Yoshi, and thank you, everyone, because I think overall we all feel that. I think there's, much as we all compete and we all do different things, sometimes we have to be somehow together and starting to point in the same direction. Otherwise, we generally end up in some degree of chaos. And the sharing of data, I still think, would be a great spot, because that could lead to the AIs of this world. Well, like everything, Helen's probably looking at the clock going, this is it, we've just blown it. What a great conversation, and we could go so much further now. You can feel the rest of the points coming out. This would have easily led to an hour in a workshop, another hour of conversation. The arguments and the debate would have swung to and fro. But thank you, everyone. I think it set the scene, and for those that have looked at or are going to look at our 5G sessions, we've already had Bob bring us into that think 5G in all this while you're thinking about this bit of chaos. It's all wrapped up together. It's all part of the same thing, and virtualization is probably the key to a safer future in the end. So thank you, everyone. Look forward to doing another session with you all at some point, and keep safe. Thank you.
Intended to no, it's not intended to kick back and listen to Bob drone on. So I'll just do a sort of opening monologue, so to speak. Feel free to interrupt or add to, and then we'll kick the discussion off. So when this was first touted as an idea for a discussion, I sort of sat down and thought, well, okay, what is a teleport? What is the cloud? And I kind of sat and thought, well, do I really actually know what the cloud is? What do we mean by the cloud? And so, you know, there are metaphors that it's just the internet. It's the internet with the ability to store stuff not on your computer and use applications that you don't necessarily have on your computer. And then you can access that same data and those files or whatever from anywhere. We do it every day with our phones, but somehow that concept hasn't quite got there with our laptops or our computer systems at work or anything. And my own company, for example, we're kind of a mishmash. We do DevOps in the cloud, but we kind of have other things which are stored on local machines, and we have to hire IT people and so on to look after stuff. And there's the rub with when we transpose that to, say, the teleport. Traditionally, the teleport is racks and racks of equipment, whether that's up converters, down converters, modems, and so on. And then we combiners and switches and so on, and then feed stuff out, and it goes to antennas or receiving things in from antennas. So what is the traditional teleport? Well, is it a gateway? Is a teleporter actually really just a satellite access point, or some of the LEO guys refer to them as satellite access points, or a satellite network port? And when you start using those kind of terms, then you suddenly think that really the satellite is kind of a network in the sky. Sometimes that network might be just a single satellite. Maybe it's HTS, so therefore it is kind of a network because you can have your service switched from beam to beam and to go to different places. Of course, the big advantage of satellite over the years has always been the single point to multi-point, single transmit to multi-beam, which is why it's so great for TV and broadcasting and so on. But with the advent of data and video on demand, how relevant is that? Well, it's still the biggest money earner for the satellite industry right now. So yeah, it's relevant and it stays and it's going to remain. But more and more we're seeing over-the-top type services, individual services, and really when you're out and about with your phone, do you really care whether your data goes over the air, goes over fiber, goes over a satellite even? What you care about is data bandwidth and latency. And I know latency, that was that big bad word for geo satellites, but that's really what you care about. And so to be relevant in the new world or new space or whatever you like, then how do we get the teleport to be a traditional teleport to be kind of relevant in that world? Well, one concept that's been touted around is making the ground digital, a digital teleport, if you like. So is that a stepping stone to the cloud? Well, if you think of the cloud as being this nefarious thing called the internet, and then the people will use different terms like edge computing and so on. So is now the teleport the edge of the cloud, or is really the teleport actually still part of the cloud because the satellite becomes part of the cloud? Dynamic payloads on satellites, although we're not yet in the geo world dynamically changing routing through satellites and so on, we're not far away. The capability is there. Are the customers really ready for it yet, or really is the industry ready for it yet? But certainly the capability is there with digital processing payloads. In the LEO world, they're really talking about although the services right now, let's take a look at Starlink and OneWeb, are really bent pipe, up, down. New constellations, if you read your FCC filings and so on, are really talking about inter-satellite links, so processing on board. So in that sense, you could say that some of the networking side anyway is moving to the sky. And then so on the ground, we get our data. And so is our new teleport the Amazon Web Services data center? You could say. AWS is very active in satellite right now. Does that mean that GCP and Azure or any of the others of that Facebook are really that far behind, or are they already active and we just don't know about it? So lots of things. So what might be the on-ramp for a teleport to get themselves ready for the cloud? Well, the first thing is thinking about how the cloud needs data as digits, and our satellite world, we're used to RF and waveforms and so on. So how do we get all of that into digits? Well, traditionally at the moment in the teleport, we down convert, we put it into a modem, and then out comes a stream of digits, and we put it into IP packets, and away we go. Does it really need to be that way? Can we take the RF signal itself and make that into IP packets and put it into the cloud, and then we can do whatever, and then we can get ready for doing whatever it is we need in the cloud? Does that mean means that the teleport changes instead of racks and racks of modems per se? It might be racks and racks of servers, and we can change our functions or create our functions, our boxes, our traditional boxes of modems and so on. Encryption devices could now be pieces of software, and once they become pieces of software, you don't need racks and racks of modems and spares and so on, because you just spin up a new demod process, or you spin up a new modulation process, and gives huge flexibility into the space. So the advantage of the cloud and what some might call virtual network functions are really all about flexibility, scalability, reliability, repeatability. And you can get there really with commodity infrastructure, which is really just computer servers. And more and more services are coming online. And it really does make the teleport ready to be integrated into software-defined network. 5G, from its very inception all the way up, is a software-defined network. There's very little hardware really in 5G. And if you look at the architecture of the radio head ends and so on, it really is all software defined. And to a certain extent, they've done what we're trying to do in satellite, which is establish a standard for transporting RF signals over IP. There are two standards really these days. There's VIDA 49, which is is prevalent in satellites. It's light on the overhead, and then there's eCPRI. eCPRI is an evolution of the original CPRI, which was around in 4G, but it essentially does the same thing. It's transporting RF over IP, and once you've got RF and IP, then hopefully the teleport does your antenna. They really need to be next to your data center, or you usually need fiber to transport from the antenna back to your data center. So in other words, a teleport could be just a bunch of antennas and a fiber bundle, or it could be a complete data center, or anything in between. Of course, traditionally teleports are in RF quiet places, so they tend to be remote, but I think that's also changing. One thing that'll really see what happens with teleports here in the States will be what happens with the compression of the C-band spectrum. We'll really find out where all those teleports are then. I suspect they're not actually too far away from populations. They're like airports. You build them out away from people, so they're not bothered by airplanes. Cities expand and move out towards the airport, and then they all complain about the noise of the airplanes. Which one was there first? And the same for teleports. So the evolution of teleports to the cloud, I think, is a natural thing that's got to come. If you think about the way I think about it, think about a service. You actually are sitting in your office and you need to send data to a colleague and maybe over the ocean on a different continent. If you want to do that by satellite, traditionally you have had to have figured out, okay, where's the nearest teleport? And where is there a teleport near where I want to send it to? Okay, can I get the data to that teleport? Is there an IP link of some kind there? And then we need to set up a service over a satellite, which means usually a phone call. And then that phone call is made and planning, and the whole service takes 3 days, maybe, if we're lucky. With 5G, I would plug in a phone number and press go, and it's done. So from a satellite perspective, how do we get there to be able to be part of that world? Otherwise, will it pass us by? And so the answer is we need to comply, I think, fit in with that software-defined networking structure, embrace the standards that 5G and the Metro Ethernet Forum are bringing in terms of controllers and orchestration. I think AT&T realized a while ago that if they wanted adoption of a single standard for orchestration, then it needed to become open source. So they put ONAP out into the open source community, and now it's been adopted. I see that SES has adopted it for what they're trying to do. And I think Intelsat's the same. I think I saw something in the press for that. So embracing, rather than competing with, embracing the 5G network and being part of that ecosystem is where I think we're going. And so teleports in the cloud, yes, I think you have to be in order to survive. Is it possible? What are all the bits that are available? Well, we have digitizers to convert to RF to IP. The other virtual network functions you might need, channelizers, combiners, switching. Well, Ethernet switches have been around for quite a while. Combiners and channelizers, they're coming. I think modem waveforms are the things that are probably the biggest sticking point right now. Is do we have enough compute power to handle large bandwidth signals, let's say 500 megasymbols? Do we have enough compute power to basically perform a demodulation and a modulation, and live in the cloud? And if we crack that nut, then I think all the elements are there. And then it's a case of willingness and evolution to move towards that world. So that's my thoughts. I thought we'd set the scene for an open discussion. Any questions, any thoughts, anyone?
Hi, Bob. It's Richard here. Standards is obviously the key thing here, because I spent about 25 years in cellular, and those guys have got it absolutely nailed, because they kind of worked out that when they got to GSM, if you get a worldwide standard and everyone builds to the same standard, then you get all the benefits of that. You know, the price of all the hardware comes down because everyone's building to the same standard, and you get the interoperability between all the pieces of the equipment, obviously particularly on the infrastructure side, and that is enforced in that world. The GSMA own that. It's like a mafia, you know, they absolutely enforce it and make sure that those 3GPP standards are adopted by everybody. So from my sort of discussions, because I was talking to people at the satellite show about this topic before it got canned early in the week, people have not yet decided, well, what standards are they going to take and who's going to force them to adopt which standards? Because at the moment, it's hard for the equipment guys to plan, because if you pick up a modem, and if they haven't got to the full VNF, the virtualized modem part, and they're still going to keep it in a modem, but if they want to put a digital interface on it, they don't know what to put on. Is it a Vita 49? Is it eCPRI? Is it the new TIA standard that's come out, the 5041 standard? People aren't sure yet what standard to apply, and it's holding people back, I think, in fully embracing it across the whole kind of equipment supply chain.
Yeah, I would totally agree. We need a standard for people to be working towards. You just look at to a certain extent, VSAT is an example of what happens with non-standards. Europe tried to make a standard with DVB-RCS, and everybody, or the equipment manufacturers, took it, adapted it, and changed it so that they were locking their own hardware in. I think they're beginning to realize that a terminal is now a commodity thing, and maybe they want a universal terminal, and really all the money is in the hubs.
Well, the reason DVB-RCS failed is because it stifled the innovation. It forced, you know, the manufacturers to stick to a very restricted, you know, list of standards, and, you know, not to be able to expand their capability of more bits per hertz and other technologies. And it just didn't make, you know, the great so-called benefits of interoperability. You know, nobody wanted, Hughes didn't want to talk to Gilad, and Gilad didn't want to talk to Viasat about, you know, testing or sharing their one modem on one hub. So it was a disaster.
Yeah, and I think coming back to Richard's point, 3GPP is a prime example of what happens when you create standards. Yes, standards sometimes can hamper complete innovation, but if you're willing to cooperate, you can innovate from within the standard. What are we talking about? Releasing release 17 sometime next year or something, over the years. And so, but the explosion in the use of handsets, shall we say, from the time that 3G came into being, and now through 4G and into 5G is a huge example that I think the satellite industry needs to go. So so you can take it from everywhere, from waveform standards all the way down through the rest of the chain, which is, you know, what are we going to transport RF over? Which one of the three competing standards are we going to use? But does it matter to a certain extent? but those we need standards that we can build to and evolve to, so that we can interoperate, at least at a level so we can interoperate with the other networks, which is really where the whole orchestration idea came from through 4G and now into 5G. Is think about how telephone calls used to work. When we first had cell phones, if Martin wanted to call me here in the States, he'd call me, and it was be recognized as an AT&T number. AT&T would figure out where the heck in the world I was and then pass the call along. So Martin would call the States, and then from the States it would say they'd go to Singapore, which is where I was. Today, because they all talk to each other, Martin would call me, AT&T would immediately say, well, he's in Singapore, and then BT or whoever he's with was immediately switch the call straight to Singapore, and becomes orchestrated and connected with the lowest possible latency and most efficient way. Essentially, I think that in the satellite world, we need to do that and to be relevant. Our advantages still apply. We have wider bandwidths on a global generic coverage basis, and those are still huge advantages over terrestrial. And then all of the other flow down elements that come associated with that. And how do we leverage that into a play into taking a bigger piece of the telecom pie, I suppose. A part of that, I suppose, is here with that cloud compute, the cloud teleport. But yes, standards, I think standards are an important part of that. And we need to get together as an industry to create those standards.
Do you think there's a lack of the concept in the first place about, you know, space taking on the 4G, 5G? Okay, we've been there and we're trying to do the cloud. So there's a more fundamental thing, I think, before you get to standards that might actually sort it out. But I want to stick with the cloud a bit, because if we assume we got the concept right and the satellite industry is finally getting its head around about how to use or what it wants out of all this and how it's going to globally connect everything, as telcos do anyway. Bob, it's quite a good analogy, really. The good old telephone call is still quite a remarkable thing in itself, right? You know, today. I was thinking about the cloud and thinking about if we had a concept of sort of cell structure everywhere. Let's just leave it at that for a minute. But the cloud can't be just a cloud, can it? I see it in three layers, really. There's an equipment cloud, the SD side of it, the software defined area where you put things, you know, your software defined modems, the equipment layer. You've got your network management layer, another piece of cloud that would actually look after the orchestration and management, the whole way things connect. And I'm not just talking about space here, I'm thinking terrestrial as well. I think it's time we stop worrying about our bit, their bit. I think the cloud has to be there because it's the only way we're going to join the two together. And the standards come from all this. We've got stuff to work with. 3GPP, as Richard said, is a brilliant place to start. As you said, Bob, modem waveforms probably a snag, but you know, once you know what you're trying to do, probably less of a snag. I'm not sure I agree with the stifling of innovation. Yes, probably to start with, but I think, as you probably everybody's thought, is if we share, it'll get over that. And then the third layer is the use bit, the data, the IoT, the do everything, the stuff. We do stuff. I remember one of our wonderful product managers saying that's what he came up. Someone asked him what he did. We do stuff. You know, I mean, it was just an enormous bag of bits and pieces they did, and that's how he thought of it. So, is anybody? I mean, we keep talking about the cloud, but I think we're going to have to talk about which layer of cloud we're going. You know, which one we're concentrating on, and which order do they come? Is it thinking about the management side of it, or is it the equipment first, then how do you manage it? Or is it the standards that build the equipment that the management comes from? The use bit's easy. Where you stick your IoT, I can understand that. That's like using Dropbox or anything else. It's a place you put data. That's what people want to do. Everything from Facebook, photographs, YouTube, and goodness knows what else. So that's my thinking, is that we probably are not in a good place because we have no ruddy concept of what we're trying to achieve. Everybody's trying to do their own thing, although that's probably starting to break down. I think we need to think about the cloud in layers, and I'm not sure I've got those right. I'm not worried about that, but I think there's a layer issue here where there are different layers of cloud to do different jobs. And that's what I'm thinking where, and the teleport sits between, you know, equipment layer. How do we move stuff about in equipment terms as software definition? And of course, network term, management terms. How do we manage that teleport? How does it connect to wherever it's got to connect to? Like you said, Bob, if you took the London to America, but you're in Singapore, if this management works well, things just connect, full stop, fastest route, whatever that might be, whatever's the best thing for your call or your piece of data, isn't it? So I'm thinking there's layers that need to be discussed, and someone's got to organise this and get things in some sort of order before we can even invent the standards. I think we're at a point where we have to really think about this, and we must be working with the telcos, the mobile guys. You know, there's no choice in this. We cannot do this. The space industry cannot manage to commercialise space without them. And if I hear any more talk about backhaul, I shall scream. I mean, that's old stuff. We need to be, if you like, front haul. We need to be in front with it, the same as the mobile terrestrial network, but in the sky, layered into it. That's it. End of speech.
I have some experience of running a cloud teleport, I guess, broadcasting. It's obviously nowhere near as big as you guys, but often, as I'm sure you're all aware, as it's kind of alluded to, often in, first of all, with the cloud, I'd rather expand this definition further and say, it's the ability for me with my credit card to go and spin up capabilities that 10 years ago were only available to nation states. And there are actually people who've done that, who've literally rented an hour of AWS and have been on the top 500 supercomputers. And that's kind of remote, and paid about $5,000 for an hour to do their genome sequencing or whatever. But going back to kind of some of my day job, we run a cloud teleport. We've received sports feeds are still widely shared over satellite, as I'm sure you're all aware. That's still the de facto way of doing it. However, many of the sports takers around the world now are not on a traditional broadcast platform. They go straight to web. DAZN's probably a big one. There are a few others. That's also kind of the same for tier 2 sports at the moment. So I'm in Singapore and want to watch Scottish football. It's not affordable to do a double satellite hop for that, but it is possible to do that over IP. So we run a cloud teleport with all the fancy Smallsat gear and whatever that you need to do that with. And it's becoming very popular for these online web platforms that literally operate entirely in the cloud. So the bit that they have to pick up are these sports feeds that still come on satellite. We get them to the cloud. They do the graphics in the cloud. They do the commentary in the cloud. Everything in society, like your mobile phone, healthcare, even heavily regulated industries, are just becoming an offshoot of the cloud, whether you like it or not. All aspects of society, well, Zoom is in the cloud. Well, we're living in the cloud at the moment, really, with COVID, whether we like it or not, and that's not going to sort of change in the near future. So from a broadcasting standpoint, like, these things are already happening. People are already doing more and more processing. COVID is accelerating this, but what the kind of processing you saw in a big physical studio with big iron equipment is being done in the cloud. With regards to the waveforms and the demodulations, very powerful FPGAs now you can get in the cloud, the same FPGAs that are in my modems, in the Novelsat modems. This is a problem that can be solved easily if there's enough market share. However, I do think it's all going to go SDR, because you see what SpaceX are doing. Look at their regulatory filings. What are they putting on the original test satellites? They're putting software-defined radios. It means they have the control of being able to do what they need to do. They can reconfigure all this stuff on the fly in space and on the ground, and it's what they're doing. I'd like to ideally move all of our infrastructure actually to some kind of software-defined thing in the future. So unfortunately, the Novelsat is one of the problems. That's obviously a closed proprietary system. But in theory, they could offer me a Novelsat in the cloud, so I could downlink all of this and get my IQs, do that in the cloud, demodulate that all in the cloud, and have to have even less hardware physically here, because that's where it's going. We're next to some 5G cell towers on the top of our building. That's what all of this stuff is going to be connected to as well. It's the future, whether, and you're not going to be able to change that, and you're not going to sort of change that from going down 1990s to telco mindsets are kind of special because they kind of have this closed ecosystem, but the rest of IT is accelerating at a very fast rate, and all even very heavily regulated industries, healthcare, defense, all moving. There's AWS Gulf Cloud, so all the stuff is changing very, very quickly, and all the whole 5-year standards processes and 10-year standards processes don't really apply when it's a cloud instance that you can spin up and spin down. Like, it's not the same as some custom CPE that there's a million different bits of CPE that can never be changed, and so it has to be gotten right first time. Like, this is very different now. Like, we in our day job with broadcast contribution, we flash and update equipment on a weekly basis. This was considered kind of outrageous even a few years ago, but customers realize they need the agility to be able to do new things in the field. And sometimes these are very complex and invasive upgrades of equipment in the field, and they need to work first time. So yeah, it's changing whether you like it or not.
So I'd like to jump in, the new guy here. I don't actually know much more about satellite and RF beyond my old ham radio license. But I do know a few things about cloud, and I think what I'm hearing is a lot of ambiguity in the definition of cloud and what it is and what it isn't. So one of the things I found helpful is in separating cloud from the internet and infrastructure is to really look at it as a process of automated scaling. If you look at the old definition of virtual machines, that was taking one piece of hardware and slicing it up to be acting like a bunch of little pieces of hardware really all hosted in one place. And cloud is the opposite of that. Cloud is infrastructure aggregation. It's saying I'm going to take a bunch of infrastructure and put a layer on top of it that's going to make all of these different components act like one big service. And so where cloud differentiates from just being the internet or infrastructure or computing or storage is in that ability to say, I've got this problem and I want to solve it without having to worry about the infrastructure details. So I can say, I want to have a whole bunch of storage and I don't care what hard drives it is. I want to have a whole bunch of compute and software services running. I don't want to have to care about where those individual things are. Where that seems to run into problems, whether it's terrestrially or in satellite, is in that topic of latency and locality. The big challenge in cloud in general is that you have to get your data from wherever it was generated, in a teleport in this case, and before today I didn't know what a teleport was, so thank you for that. But you have to get it to that infrastructure, and that's where the whole cloud scaling becomes a challenge, and where I've seen a lot of my own customers really run into trouble is not taking into account the latency issues of getting the data from some one point to whatever that cloud infrastructure is. So cloud is great for automating and scaling, but always the challenge is that the data has to move. And of course in satellite, I know we have a lot of customers on satellite. What we actually do, by the way, quick background, is we make software to accelerate data transfer. And so when we move data from point A to point B, our goal is to get full bandwidth regardless of the distance involved. But that distance is still always a factor. The networks, the congestion, everything is always a factor. So I think what might be helpful here in the satellite venue is looking at, you've got the satellite up there, you've got your latency coming down to the teleport point. And then when you go into the cloud, that gives you tremendous ability to do software-defined infrastructure, software-defined scaling, but you still have to get the data from that teleport point to wherever that cloud infrastructure is. And that's where I think what I'm hearing is that some sort of standards can become very helpful. In terms of how that translation from RF to IP works, and then in terms of the mechanisms by which you coordinate where that goes. You want to. I'm going to take some risks here on not understanding the terminology fully, but you're going to take a digitized RF signal and you're going to move it to some compute location somewhere. So which software are you going to have there that is going to be available to demodulate that, to translate that into something else? and what's the delay going to be in getting it there, and then what standards do you need to get that to the next point in the processing and the workflow to translate from ultimately an RF signal, for example, to a an H.265 stream. At each point there's a translation, and cloud makes it a lot easier to experiment with that. It makes it a lot easier to scale that up and down, but there's still always going to be that kind of linear problem of at each step, how do you translate from one to another, and how much delay do you add as you add those layers up.
Seth, can I ask a question? You said something interesting there about data optimization or acceleration. Sorry if I misrepresented it, but that's kind of what I understood. Bob sort of highlighted one of the key advantages that satellite has over terrestrial, and that is the gargantuan amounts of bandwidth available to the satellite world. So if we look at like Ka band at the moment, it's a bandwidth that's up to around 4 gigahertz wide. If we just translated one of those gigahertz into the digital world, just one gigahertz line is about 100 gigabit Ethernet line. So if you've got 4 of them, then you're at 400 gigabit Ethernet. And then if you're up to looking at uplink and downlink, and then 2 polarizations, we're looking at lots of gigabit Ethernet. How do we get that to the satellite scale, working efficiently in an IP world?
Yeah, so it's really hard to compare because it's hard to compare one line in the satellite world to, say, a network in the terrestrial world, because of course the network in the terrestrial world is never just one line, it's many lines in parallel. And one of the big challenges that I've seen in translating networking from what folks on the infrastructure side see to what folks on the use side see is the notion, are you talking about one thing happening at a time or many things happening at a time? For example, when I go out to customers and I talk about, how fast something is, I'm talking about how many gigabits per second, I always think of it in terms of, well, I'm of one thing at a time. I'm transferring one file, I'm transferring one cloud object. But when you talk to telecom people, they're talking about many things at a time. They say, I got a 100 gigabit network. Well, nothing on that network is moving at 100 gigabits per second. There's 1,000 things running at 100 megabits per second, for example. And so when you talk about scaling bandwidth and making use of bandwidth, the first question to ask is, how many different things are going on at once, and what's the average user experience? It makes a lot of sense when you're thinking in terms of video streams, for example. If you've got a over-the-top video stream, high definition, say it's a couple of megabits per second, it's fairly fixed rate. So how many of those can you fit on a 100 gigabit line? On the other hand, if you're talking about somebody, say a oil and gas exploration company, they've got a terabyte of mud logging data that they need to move around for analysis. Well, they need just as much freaking bandwidth as they can get for one big blob of data. And so it's a different scenario. And it's, satellite, if you can get 100 gigabits per second on a single line, that's going to appeal to a different audience than, say, in a terrestrial world where, well, okay, you may not have, 100 gigabits or a terabit on any one data stream, but you can spread it out into a bunch of different places. So I don't know if that answers your question, but that's sort of one of the sticking points I see, is that sort of one versus many.
Yeah. I suppose because the satellite world's used to having obviously with TV broadcast, it's a very set amount of data usage, but moving towards, mobile communications and IP type traffic for those types of users, it's, as you say, it's bursty and different depending on what they're running.
Yeah, and like one of the really big things that we often have to educate our customers on is the difference between that fixed rate versus bursty transfer. If your goal is to have something that is rate set at the source, like video or a telephone call, then there really isn't anything concerned about acceleration. It's going the speed it's going. You just don't want it to get messed up or have anything lost along the way, but it's really there about steadiness and reliability. Whereas if your goal is to move a big blob of data from point A to point B as fast as possible, then it's about filling the pipe. And those are two very different user experiences. They require very different software. For example, my company is focused on the bursty side. We get the data there as fast as possible, but somebody comes to me and says, hey, I've got a data stream that's, video, it's 2 megabits per second. I want it to be steady. Well, that's not me. That's somebody else that's going to do that. But from the end user standpoint, the guy sitting there with his phone, he thinks in terms of, well, I'm watching Netflix or I'm looking at a website. The user doesn't care about the difference, even though it's a completely different use scenario underneath and requires different infrastructure.
Okay. Thanks, Seth. Thank you.
It is
I think
interesting.
trying to summarize what. Oh, sorry. Go on, Andrew.
I'm going to say it is interesting, isn't it? That I know what Martin was saying before, and also Richard said very very clearly about the requirement for standards across the networks, and it's something we've never really been able to get to. We've always been proprietary in our approach across each of the individual satellite operators. It is very different depending on which regional or global network that you're using. And what I found interesting, just hearing some of the conversation here today, and especially what you've just said, Seth, a few minutes ago, one of the things that we're going through, it's a change we don't talk about that much, actually, at least not as often as I think we need to. We're in a situation with our industry now where revenue is going to reduce significantly, because we've been used to doing that one-to-many broadcast type. You have this much bandwidth, you use it as you like. I know there's some differences with statistical multiplexing, but generally that's what it is. And we're probably on the cusp of the biggest change in the industry for 50 years. And that is, we're moving to a different kind of satellite, which is high throughput, and is able to use the frequencies over and over again, but it doesn't lend itself to our core cash cow of developing direct-to-home TV. So that stifles us in actually competing against the Netflixes and the Amazons of the world a little bit. We're also moving into an area where we're going to be looking at LEO and MEO constellations, and neither of those lend themselves to TV distribution in the same way. So we're at a really difficult point in that we've got some great technology, but we're almost back at the beginning. We don't really know what to do with it, whether we deliver that one-to-many, if we can, fat band thing that's brought us in all the money over the years, or whether we look to the more bursty markets. And it takes us a long time as an industry to settle on any standard that we can all agree to. Recently, I know Ellen and certainly Martin will know about a group called the SOMAP group, or the SOMAP idea, which is a standard minimum operational specification for antennas. Now that's taken something like 3 years to come to fruition. And although it's now been established a year ago, September, we've really not got that out into the marketplace. Now that's only one small part of what we do across the industry. We now all agree on what should be the minimum operation for the antenna itself. We haven't really told anybody yet. So the bigger things that we need to look at in terms of interoperability, I don't even think we've scratched the surface. I may be being a bit mean there. Please come back at me and say I'm wrong. But I think what Richard said earlier, why can't we get to a standard that we apply across all networks so we can all benefit from it? It seems crazy to me.
I can tell you what I would really like out of satellite is if I have, an office, a data center, what have you, and suddenly I need to move a lot of data. Like right now, if I have to go to a telecom company and get a 1 gig, or God help me, a 10 gig or forget about it, 100 gig line dropped in right now, that's going to take months. And if I could instead hang a satellite dish out my window and get 100 gigabit per second connection, now you're going to have a lot of customers, because that kind of flexibility, and you want to talk about cloud and infrastructure flexibility, if you could deliver that kind of ability to drop bandwidth anywhere in the world quickly, there are a lot of people who are going to pay a lot of money for that, just because of the fact that, you know, even though it may be more expensive in the long run, I see a lot of projects where, and this ties directly into cloud migration. You've got a data center, they got a gigabit connection to the internet, but they need to move a petabyte of data. There's a lot of petabytes of data out there, and it's going to take them a few months, and then they're going to be done with that, and they're not going to need that high speed anymore. But if you could tell somebody, I mean, look at AWS. They've got this thing called Snowmobile. It's an 18-wheeler full of hard drives. That's how badly people need to move data, and how badly current terrestrial telecom is doing at servicing that industry. So if you tell me you can deliver a 100 gigabit connection somewhere, if your standards can drop that to a dish that I can hang out my window and have it set up and running in 3 days, there's going to be a lot of people interested in that.
Yeah, if we could do that, none of us would be on this call, Seth.
I think we need Seth and Kieran and John talking to our industry just themselves. I think that would give us a bit more inspiration, a bit more feeling about using what we're trying to do here. I think I'm with Amber. I don't know whether it's just you and me, Amber, but I mean, whether we're the ones that are a bit slow of the brain cells these days, but I do think our industry is horribly slow. It doesn't have the basics in mind. It hasn't cottoned on to what Seth wants, which seems a shame, because it's something we could probably deliver. I'm not sure about 100 gig yet, but it, you know, we haven't worked on it. So there's a thought. We've got all this HTS sitting up there, and to be honest with you, it's not being used right now. Not really.
Well, that's interesting. Angela, do you have a view on that? Because you're the satellite operator. I've been with one in the past, so sorry to throw you the cudgel here, but could you comment on that? Am I misrepresenting it at all?
Yeah, so I mean, I think what we're speaking about, there's two major aspects to that where we're you know, I think a lot of the satellite operators are focusing is we are moving towards the high throughput satellites, and that makes us able to put bandwidth down on a fairly quickly basis in specific regions as needed, and then to retract and pull that bandwidth back as needed as well. But we're also putting a lot of efforts into traffic shaping. So in talking about looking at voice over IP and streaming video, obviously there's where we need, you know, we need to make sure that we're cognizant of the latency. But there's lots of other types of data that's being processed, and maybe processed from the same devices or similar devices going across similar routers. It's that can be shaped and moved in different ways where latency is not so much of an issue. And I think that that's where a lot of the focus is going, and those that aren't focusing there probably need to move in that direction as well.
Interesting.
Yeah, just to kind of, well, I'm going to have to drop off in a few minutes, but to kind of wrap up from my thoughts, coming back to Martin's idea that this whole idea of the cloud teleport, it is a layered approach. And where we're talking about standards, or at least from my perspective, some standards in the orchestration. So we have to have the same interfaces if we're going to be part of the greater software-defined network. Which allows for automation of services to be connected. It also allows for the greater adaptability and the greater use of the software-defined, well, not necessarily software-defined payloads, but let's reuse that term for now, which is the flexible payloads which are coming with the latest and greatest HTS satellites. So essentially machine-to-machine service configuration and setup and teardown, rather than the old manual way of doing things, which really, and so there are standards already set with 3GPP through Metro Ethernet Forum, which all of the terrestrial people are using. And I think that's probably no surprise why SES and Intelsat have announced that they're going ONAP and that kind of route. And that gives them a huge advantage over their, say, competitors in terms of maximizing the benefits of their configurable payloads, shall we say. So for the teleports on the ground to take advantage of that, then they need to equally be software definable. So that's where that kind of standard comes in. The other part of where I think the standard comes in is in terms of the waveform. Think about it today. So you've moved a service from DVB-S2 to DVB-S2X. Oh, crikey, where am I going to download that, to which teleport? Oh, well, I've got a bank of DVB-S2 modems, but I don't have any DVB-S2X modems. I've got them on order and it's going to take 3 months. Whereas if it was already in the cloud, it was just a case download it from the app store, so to speak, and spin it up and away I go. Oh, well, I now need 3 of them. Excellent. I'll just copy them and spin up 3. And that's so in terms of the standards in the waveform, it allows those waveforms to be created. Whereas if they're bespoke, it becomes back to Richard's point, the cost. It becomes a cost driver if everybody's got different waveforms. Whereas if you can just go to and get a generic DVB-S2X DMOD process, for example, and we are going to need more DMOD processes than we are going to need mod processes. I think that's just the way satellite works. So those are the standards.
I'm sorry to interrupt, but so if Novelsat had an NS4 app that I could spin up because Formula One needs NS4, but then most of it, and it cost me twice as much for 2 hours a week, and then DVB-S are used for the rest of the week. Why is that kind of a major problem? Because that's how it is at the moment with existing cloud technologies. You know, if you need to use something proprietary, you spin it up for an hour, and then if you want to use something non-proprietary, you just use that for the rest of your time. If that kind of business model exists today, and it's a nightmare with physical equipment, but in the cloud, that's less of an issue.
I would agree that it becomes less of an issue, but if you're trying to transport those waveforms through satellite, you've also got to modulate them that way. If the source is already there, then yeah, that's true. But I think if we're going to create a greater, larger network in the sky, we probably ought to at least have some basic standards of what those waveforms are going to be rather than proprietary. Or every proprietary generator of waveforms is going to have to make their apps available in the app cloud store so that teleports can download them and use them.
What's wrong with that? That's kind of the way it is already, right? Like if I want to buy an NS4 box, I can. If I want to buy another proprietary waveform device, I can, but it takes 2 months and gets stuck in customs like ours did. But you get there in the end. But if that's a point and click process, it's less of an issue, you know?
Well, that's true on the teleport side, but the traffic generation, let's take aeroplanes. It takes probably 2 years to approve a modem that goes onto an airplane. And once that's done, it's done.
If it's an FDR modem that can be reprogrammed, it's getting very cheap now to do that. Can be reprogrammed on the fly. Reprogram the FPGA. It's kind of what I said in the chat. Like a lot of this is based around fixed function hardware that needs to be replaced in 5 to 10 years. And if that just becomes a much more open and reprogrammable interface. So in our company, in broadcasting, we have this problem with SDI, for example. All of the equipment in the marketplace was not reprogrammable in the field. You were dependent on the vendor. So we spent, by our standards, a considerable amount of money building something ourselves that was reprogrammable in the field. And could this translate to what you do with modems?
Yeah, great. There are still requirements on aeroplanes about loading in the FPGA. So there's still an approval process. It's not quite as flexible as you might think. Also, cost-wise, they tend not to want to have to buy a $5,000 FPGA when you can get an ASIC for $500 to put into if you're going to talk about volume. If we're talking about getting to endpoint, look at what happened with set-top boxes for TV and so on. It really was. Then translate that into our cell phones. How many? What's the multiplier of modems in the cell phone?
Can't get Netflix anymore. Like that's the problem. Those $20, my $20 set-top box. When you press it, it goes oh, you can't get Netflix, this is now out of date, because it's not a fixed function device. Whereas you look at smart TVs, they're much more powerful, much more reprogrammable on the fly. You know, the Disney Plus app appeared, was it 3 months ago? Now I can get Disney Plus on my smart TV, whereas I can't get that on my Skybox and my other low power, poor, you know, cheaper devices. You could say for that one narrow use case 10 to 15 years ago, it was really great that we could have DVB-T2, which was, you know, world-class modulation, but the world changed. And so it's much more important now to have reprogrammable and flexible devices than it is to save a few pennies. And I think consumers are already seeing that. You could argue that it's right that hardware manufacturers want everyone to dump their equipment after 3 or 4 years, and there's whole ethical issues around waste and whatever. But the cloud is a classic example in terms of you reprogram that hardware every few hours. It's where things are going. The cost is an issue. I'll give you that for consumer devices, but in a B2B environment, there's no reason why this stuff can't be reprogrammable on the fly. There's no reason why I shouldn't be able to log into that Smallsat device and reprogram whatever I want into that device, not be locked into them. And that's already possible in the cloud. As I mentioned in the chat, imagine Amazon forced you to use their software in AWS. It wouldn't be a successful service. And that's one of the reasons AWS is successful, because it doesn't force you to use software, you know, the software that you want. You can spin up and spin down other people's software at scale. And if you really want that to work at least in a B2B world, B2C, yeah, different ballgame. But though Netflix and others are maybe changing that because they will have requirements. So the classic one at the moment, Netflix will require, and YouTube will require AV1 in all receivers. So you're going to have an AV1 decoder in all your receivers, whether that's software or hardware. Nowadays, actually, software receivers are like really fast. My TV has a faster CPU than my phone. That's not a big issue, but reprogrammability is going to be the thing, as consumers will require a new thing every 3 months, not every 3 years now.
So quick interjection. I'm hearing a bit of a disconnect between where things are happening. So when you talk about software-defined modulation, it matters whether that happens, for example, in AWS cloud versus at the point of the teleport. Because if the teleport is not in an AWS data center, then you've got to move that over IP. And so if you've got, say 100 gigabits coming down from a satellite, and again, I don't know if that's a realistic number, but even 1 gigabit coming down. It's a bit high, but yeah. I mean, gigabit into many data centers is very cheap. I have a gigabit line that I'm not using at the moment. It's very cheap. I didn't even bother to cancel it. There's no sports going on. Didn't even bother to cancel it. It's very cheap in many cities. The bit that you need to care about is how do you interface the cloud, which has tons of connectivity. Teleports, and many teleports I've been to have so much dark fiber in the ground I couldn't even, more than you can shake a stick at. It's how do you connect those teleports to the cloud and to these remote locations where satellite really will benefit. How do you make the cloud and the edge point for this? I'm an oil well, and I have all these camera feeds, I've got all this data. I need to compress it, get it up, process it in the cloud, and then bring it back to get my results. This kind of thing, not trunk the whole thing, not trunk the whole thing into the cloud.
But I really do have to drop off. I completely agree. The cloud gives you complete flexibility for different types of services and so on going forward, and it does mean that if proprietary waveforms come up, then that's great. But the thing to bear in mind is these waveforms have to go through amplifiers, and each time you change a waveform, you change the peak to average power ratio. Amplifiers are getting wider and wider bandwidth. For instance, I think at KA band now that the amplifiers are 2 gigs wide, at least on the satellite, if not wider. And that's more than one waveform going through it. And if you look at 32 APSK or 64 APSK, they kind of have 10 dBs of peak to average power ratio. Put 3 of those things through, and those amplifiers suddenly start getting backed off quite a bit. So there is a need for defining what waveforms we are using with a low peak to average power ratio. That's the big thing. The sharper we make the roll-offs on waveforms, if you're going from 0.25 shaping factor to 0.05, for example, you're adding 2 to 3 dBs of peak to average power ratio. Yep. It's just the way it goes. You don't get something for nothing. So we have to be cognizant of what happens to the amplifiers in the sky, which also means the amplifiers of the teleports. But yes, cloud gives us huge flexibility to do that. But in terms of, from a satellite operator perspective, I think they're looking for standards in terms of the waveform so they can manage their amplifiers, which is really what they're interested in. and data throughput. We're getting more and more into bits per hertz as a discussion. We used to talk about PEB, power equivalent bandwidth, power and bandwidth. Now we're talking about bits per hertz. You know, and if the best we can get with DVB-S2X is 5.7 bits per hertz, and then I've looked at 5G and they're talking about 10 to 15 bits per hertz, and you think, wow, okay, what are we missing? Well, you know, we don't have MIMO for a start, but they do have other powerful techniques, and yes, software defined allows us to then start using that innovation. But in terms of managing amplifiers in the sky, there needs to be some kind of regulation and standards of those waveforms going through, because you don't want to be pulsing into compression and then you actually lose your bandwidth because you're creating errors and so on. With that, I have to sign off, but you guys, I look forward to listening to the rest of this online. Thank you.
Thanks, you, Bob.
Thanks, Bob. Wouldn't this have made a wonderful live workshop? Eh? I mean, this is, you've done really well here. I mean, we've taken the cloud and ripped it up a bit. And as I say, thanks to Kieran and Seth and John for sort of changing our views and adding a bit more pressure into this conversation. It's interesting that Bob brought us back to the dear old waveforms and the amplifiers. Yes, we have to, so physics, the laws of physics are still with us, sadly. So there is a compromise, but I mean, it's, yes, software definition has got to be the way forward. I mean, it is anyway. And the quicker the modems become just that, just a piece of software somewhere, the better. It's interesting. Does anybody know who's actually doing that? I mean, out of the big now ST engineering, surely that's where they must be heading. Does anybody know that for sure?
The software inside. They're FPGA accelerated, but my understanding is their software, because they did a big upgrade from NS3 to NS4 in the field. And in fact, I just saw ours turn to NS4 one day. And that was a pretty substantial change from what I understand. Like,
okay. Good.
But that's very high. That's the highest end of the highest end. Like, it's Formula One, it's the Premier League. That's not for Joe Public per se.
No. But like you said, if you could spin this stuff up and spin it down again, if we go to Seth's idea where he's saying, I just want something now, quick.
Yeah.
I want stuff moved from A to B. I want things done like that. Seth's saying there's another business model there that we're not exploiting.
I agree. Formula One is an hour a week. It's 2 hours a week. Why is this device sitting there for Formula One doing nothing for the other 300 and something days a year? If I could spin that up and pay $10 an hour and all of you could spin that up, that's much cheaper than them trying to ship these boxes around the world and having to get them stuck in customs. I mean, it's so much simpler.
And then Seth will want it all for a month. Yeah.
it's not impossible, actually, Kieran. I mean, you remember when we went from analog to digital back in whenever it was, 97-ish?
Yeah.
And Intelsat, Eutelsat, AsiaSat, and all the satellite operators sat down under the umbrella of the ISOG, you remember? And we defined what a TV channel would look like in 9 megahertz of bandwidth for an occasional use television transmission. You know, what the data throughput would be, what the Reed Solomon would be, and everybody adhered to that worldwide. And at that point, you could actually do exactly what you're saying, Kieran. You could go to Eutelsat, you could go to Intelsat and say, I want to know U channel for a TV thing, and everything worked well with it. And then we started to get a little bit fancier with our encoding and our modulation and so on. And we kind of got away from that standard approach. But for many years, that served as well. Martin, you must remember that being brought in. I remember being at the ISOG in, I think, 98 when that was all signed off. And it worked brilliantly. You know, it's, I guess we don't just have the same standard anymore for a standard TV, standard data throughput channel.
I guess it was the Eurovision
channel for that.
Yeah, I mean Eurovision.
No one's willing to pay Eurovision prices anymore. So
yeah, well,
no one's willing to pay for 9 megahertz anymore when they can do it in 4.5 anymore.
Exactly.
You see bit rates drop. But anyway, now COVID's going to change that even more because people are going to be used to Zoom calls from people's houses. So it's going to get even worse. Like it's going to be whatever 2.2. I don't know if you can do half or 4.5, but it's going to get maybe 8 megabits will be a standard for HD, something like that. That's going to get normal now because the world is getting used to it.
Yeah, of course not.
Because there's a reality of finances. That's going to change. You'll probably also see hybrid satellite IP. That's happening a lot for occasional use, where the IP will be prioritized. So 4G and 5G will be prioritized, and then satellite will be the last resort. That's becoming very common. There's also the fun one of occasional use over KA backgrounds, which I know Eutelsat are big fans of. People are doing a lot of that, so just using the background service instead of the premium service.
Yeah.
To do that, and that's becoming a thing because people are watching on mobile devices where they can't see the difference. So it's not really a big issue in that respect.
That's where I think I come back to where I was coming from originally, which was not really about the cloud. Really, it's like the stage before the cloud. Is that our industry, and I'm talking about the satellite side now, there's no bloody concept of what it's really up to. It's got no idea about the real core use cases. It's always looking to be in background. It's always, like I said, we use the word backhaul. It's always back up. It's always a little bit here and a little bit there. It's not forward thinking in saying we need to be a part of this. And I think if the world wants to connect itself, especially now, the way we are now, and people probably will not travel as much, especially business-wise. I see the big change there. We know it's happening, not just in our industry, but across, where people are not going to bother to travel to shows and things anymore because there's just no point. They've suddenly realised the obvious, which I guess some of us have often thought about, but, COVID has certainly... once the Zooms and the go-to meetings and everything get better, and they need some improving too, and all our internets and all the different connection layers that we need from rural offices to city offices, town offices, whatever they are, things aren't going to be the same. I think, Kieran, you're right. The world's changed and it isn't going back. And
but interestingly, Martin, I would have liked to have been in the beginning of year marketing discussion at Zoom to say, now what we're going to do this year to get the products out there, because that would have been bloody hilarious. But
anyway,
yes. But we have had some moments of innovation with the cloud within the business to business side of the business, because it must be 3 or 4 years ago, before Elemental was subsumed by AWS. I was working in a teleport where we were able to buy sufficient encoders for our normal run of business. But when we had an exigency like Commonwealth Games or an Olympic Games, we didn't have to buy more hardware. They simply let us use their services in the cloud for the period that we needed it. And I thought that was one of the first really smart moves of how to use the cloud within the industry. And that was for our encoding. And then after we'd finished the thing, we just went back to our normal hardware approach.
Thank you everyone for the interesting discussion. It is clear that the satellite industry needs to adapt to cloud working. Transition for many to the cloud is already underway and our industry needs to be on board. At the same time, a number of questions remain unanswered. The industry needs to consider standardization, security, modulation, and RF over IP infrastructure in order to move towards a cloud-based mindset. I look forward to seeing how this evolves.